Well, welcome everybody to this week's distinguished lecture. My name is Jeff McDonald, and on behalf of the Global Institute for Water Security and Global Water Futures program that underwrite this series, it's my pleasure to welcome Deb Perrone to our group. Before we get started, I want to just note that next week is Ross Woods coming to us from Bristol University in the UK. And also, before we get started, to acknowledge that we're on Treaty 6 territory, homeland of the Métis, and we pay our respect to the First Nations and Métis ancestors of this place and reaffirm our relationship with one another. It's my real pleasure to introduce Deb. She's an assistant professor at UC Santa Barbara in the Environmental Studies program, and she's also a non-resident fellow at Stanford University's Water in the West program. Deb did her PhD at Vanderbilt University with George Hornberger, who many of the people listening will know, and she received the Founders Medal for that PhD. And after her PhD, she continued on and did a postdoc at Stanford before transitioning to Santa Barbara. In the 6 years since her PhD, Deb has exploded onto the scene and is really a young superstar in the field of groundwater and hydrology generally. Fully a quarter of her 20-odd papers that I see in her CV are in high-impact journals, like the one we're going to read for Journal Club today, in Nature Sustainability. But it's quite remarkable what she's achieved in a short period of time, in addition to recently completing a textbook with George called Water Resources, Science and Society. And I think what makes Deb a real thought leader is her rather unique ability to tie together water quality, water quantity, and policy science in a way that I've just not seen done before. So it's such an honor to have Deb with us, and we're looking forward to your talk, Deb, and I'm going to turn it over to you now. Thank you.
So before I begin, I wanted to thank you for the invitation to speak today. I'm honored to be part of this distinguished lecture series and also to be part of the discussion on breakthroughs in water security. This is a topic near and dear to my heart and also part of the passion that really drives my research. So today I'm going to be talking about groundwater wells. I thought I would start out with a picture of a groundwater well, and what you see here is it's sort of lost amongst the landscape. I really like to point this out because for me, groundwater is often considered this hidden or invisible resource. And it's not only the resource that's hidden, but it's often the infrastructure too. And so you can contrast this groundwater well with the infrastructure that you tend to see for surface water. So big dams, conveyance systems, those are things that you see really readily. Whereas groundwater hidden beneath the surface and then infrastructure, groundwater wells, sort of lost amongst the landscape. And so I thought it would just be, a perfect way to start this talk by giving a visual of what I'm going to be speaking about today. Now, despite the solitary vision that this picture portrays, the work that I'm going to be presenting today is in collaboration with Scott Giesecco, Rebecca Nelson, Derek Wynn, Grant Ferguson, and Jennifer McIntosh. Today, I'm going to be talking about groundwater, and I'm going to be sharing a story of an overlooked resource and how we can leverage hidden data to promote our understanding of both the challenges and the solutions. Like I said on the previous slide, groundwater is often considered an invisible resource, hidden beneath our feet. While groundwater may be stored under our feet and hidden from our sight, when it comes to the surface, it provides more than half of the global population with drinking water. Groundwater also provides more than 40% of the water that's used for irrigated agriculture. This map here shows the irrigated area serviced by groundwater in percentage. And you see that there's a few places that really pop. So we have China, India, the Middle East, and of course, the United States. And it's the United States that I'm going to focus on today. So there's no doubt that groundwater is an important resource. There's also no doubt that we are overusing groundwater in many places throughout the United States. And so there are a lot of undesirable results that are linked to groundwater depletion. We know land subsidence, saltwater intrusion. These undesirable results have been studied significantly throughout the literature, but there's one manifestation of groundwater depletion that prior to the studies that we've been doing has had little attention beyond the media, and that's when groundwater wells run dry. And so for those of you in the audience that are new to groundwater, you're probably asking, when do groundwater wells run dry? Well, groundwater wells run dry when we have declining groundwater levels to such an extent that a pump can no longer lift water to the surface. But until recently, it's been really difficult to understand where groundwater wells are running dry. And one of the reasons for that is because well drilling is rarely studied. So what does this mean in layperson terms? Well, this means that until recently, we didn't know where groundwater wells were constructed, the reasons for which they were constructed, and the depths to which they were constructed. Now, one of the reasons for this is because water quantity is mostly the matter of state law. So again, what does that mean in layperson terms? That means that each state, and in some cases, sub-state areas, groundwater is collected and put together in different ways. And so the map that you're seeing here shows a number of the different biases that we encountered while collecting these data. And so it's really important to point out here that it's not necessarily that states lack information about groundwater, because many of them, groundwater wells, because many of them actually have quite a bit of information about groundwater wells. It's more that this information has not been stitched together to give us a continental scale picture. So for the past 5 years, we started collecting groundwater well data in all of these states and in sub-state areas. And by exploring these well reports, we were able to put together big data of what we're calling local relevance, providing really important insights to both the hydrogeological conditions, but also really important insights on groundwater user decision making. I thought I'd start out with this map because it really highlights the extent of groundwater wells in the United States. So here I'm showing 11.8 million groundwater wells, where each one of these small tiny dots that you're seeing is marking a groundwater well that was constructed between 1950 and 2015. This map shows the reasons for which groundwater wells were constructed, and there are a lot of different reasons, but we broke them down into 3 key categories. What we found is that 83% of groundwater wells indicated that a well was constructed for domestic or municipal purposes, and we broadly categorize this as domestic. 15% for irrigated agriculture, and the remaining 2% for industry. Groundwater well reports also provide really important information about the depths to which wells are constructed. And so this map here shows in light blue shallower wells and in dark blue deeper wells. And it's really important to point out here that before this map, our understanding of how deep people were drilling wells was usually constrained to local or regional studies or anecdotal information. So with this information, we've been able to indicate that the average groundwater well across the United States is about 60 meters deep, and the median is about 44 meters deep. Now, looking at this map, a lot of you who are familiar with groundwater are probably not surprised that we have deep wells in places that are known for agricultural production and unfortunately also known for groundwater depletion. But there's some really interesting, new areas that pop out, especially for folks who are not necessarily studying groundwater in the Midwest. So really deep wells underlying the Ozark Plateau. We have shallow wells near the Great Lakes. And not surprising again to those of you who study hydrogeology, but shallow wells near our rivers. And so we could use this information about groundwater wells to try to figure out where wells were running dry during the last drought. And so for this particular study, we focused on the Western 17 states. And what we found is in the Western 17 states, on average, 1 in 30 groundwater wells ran dry during the most recent drought. These wells were concentrated in areas of high agricultural production, but specifically in rural communities. And this is really important because what we found is that rural communities are really bearing the brunt of the impact of groundwater depletion. Rural communities are often isolated from urban infrastructure, and they're more likely to rely solely on groundwater. Now, this has become especially a really, emotional point in California. And I thought that there'd be no better way to really show what's going on here than to show a video of people that are actually experiencing their wells run dry.
Now is a lot of the homes, the majority of the homes, have their own private well system, which feeds water to their home, and those wells are all drying up.
It is absolutely an emergency. Tulare County is really ground zero for the drought in California. Approximately 55 to 60% of the dry wells in California are in Tulare County, with the majority of those wells being in this specific area of East Porterville.
Unless it directly affects you or someone you love, you don't understand what these people are going through.
And so I really think that it's, this video that brings home how important it is to understand what's happening with water scarcity and how that manifests through to people losing access to safe, fresh water. And there's one thing that I really like to point out after watching this video. We are in America, so in one of the richest countries in the world. We're in California, a state that by some accounts is within today's top 10 economies in the world. And yet there are still people who are losing access to safe, fresh drinking water. And I really think this drives home sort of one of the biggest, wickedest challenges that we're facing with regard to water scarcity, somebody's well running dry. And so the question that I've asked here is, what can we do when the wells run dry? And how can we use the immense amount of observational data that we've collected and that you've seen in the previous slides to highlight this challenge, but to also highlight opportunities available to get us to sustainable groundwater management? So we have information about groundwater wells, and the question that we asked here is, are people drilling deeper wells over time? Now, it may seem like common sense. If your well runs dry, why wouldn't you drill a deeper groundwater well? But let's explore that, and let's explore that across the United States. So again, we have information about groundwater well location and depth. And what we also found is that groundwater well reports provide temporal information. So this allows us to look at time series of depth trends. Here's an example near Stockton, California. Across the x-axis, we have time. Across the y-axis, we have depth in meters below the land surface. Each one of these dots indicates a constructed groundwater well during this period of interest. So for the one that I've highlighted in blue, this well was constructed in the year 2000 at a depth of 100 meters. So we could do the same exact analysis for the entire United States. What we could do is we could group the United States into a number of different grids, 10 kilometer by 10 kilometer grids in this case. We also broke down the analysis into a number of different time periods, mostly to account for variations in the database. So if you remember a few slides ago, I really highlighted that because water quantity is a matter of state law, we have a lot of different biases in how folks collected data. And so we wanted to make sure that we accounted for that. We use this information to calculate Spearman rank correlations. We use Spearman rank correlations instead of Pearson correlations because they're more resistant to atypical values and the nonlinearities that could arise because of the heterogeneities of the subsurface. We made sure that each of our different grids had at least 10 groundwater wells during the time period of interest. So going back to our Stockton, California example, we'd be looking at the trends during specific periods as I've highlighted here. Now, to make sure that we were not susceptible to any biases in the way that we grouped using grids, we also ran a second analysis using polygons optimized to have 100 wells. In layperson's terms, basically what we did was we identified a whole bunch of areas through ArcGIS that had at least 100 groundwater wells, and we were able to optimize that throughout the United States. So on the left-hand side here, you're looking at the results for 10-kilometer by 10-kilometer grids using the 3 periods that I've outlined in the previous slide. So 1950 to 1975, 1975 to 2000, and 2000 to 2015. On the right-hand side, you see the polygons, again, for that same time period. Anything that's gray indicates that we're seeing little to no trend in depth over time. The orange and the red indicate that we're getting deeper over time. The blue indicates that we're getting shallower over time, and some really interesting trends right there in the northern high plains. And then the white indicates that we didn't have enough data in those states to analyze it during the time period of interest. So even with a quick view, I know that the grids on the left-hand side are extremely small, so I really like to look at the right-hand side, the polygons. Even with a quick view, you could see that there's more red and orange than there is blue. So there's more places where we are drilling deeper groundwater wells than we are drilling shallower groundwater wells. And this holds true through a number of different scenarios. So here you could see that we extended to a number of different time periods. And the big take-home message here is that the percentage of grids or polygons that show deepening trends are greater than the percentage of grids that show shallowing trends. And that really holds true even if we look at significant trends only. And so what does this mean? Well, the big take-home message here is that well deepening trends are 1.4 to 9.2 times more common than well shallowing trends. So no matter how you slice it, what time periods, what areas you look at, we are drilling deeper more often than we are drilling shallower in the United States. And so we have information about drilling deeper. Now the question is, how can we combine that with information about declining water levels to get a better understanding of the relationship between the two? So what's unique about this data is that we were able to see continental scale hotspots as well as locally relevant information. So the map on the left shows groundwater depletion in key aquifers, where yellow and red indicates significant depletion since 1900. The map on the right shows our groundwater well data. And what is really cool here is that we can use this local scale water data to start addressing continental scale water challenges like declining water levels and depletion. So you've seen in the past slides that we have information about groundwater well construction. We can pair that information with groundwater level data from monitoring wells. On the right here, you see that there's a satellite image. The blue dot in the middle indicates a monitoring well with water levels, in this case, between 1950 and 2015. All of those yellow circles that you're seeing indicate a constructed groundwater well between 1950 and 2015 within a 5-kilometer buffer. So for the analyses that you're going to see moving forward, we picked a 5-kilometer buffer as sort of a Goldilocks approach. We wanted a big enough buffer that we'd be able to get a statistical sample to run our analyses, but a small enough buffer that we'd be able to pick up some of the local subsurface heterogeneity. So let's go back to our example in Stockton, California. This blue area here shows the water level time series. And over the period of interest, so 1950 to 2015, what we see is that water levels are declining at a rate of 3 meters per decade. Each of these yellow dots indicates a constructed groundwater well during that same period within that 5-kilometer buffer of the monitoring well. Over the period of interest, we see that groundwater wells are being constructed deeper at a rate of 7 meters per decade. Now, this is really exciting to me because I'm really fascinated about the human dimension component of water scarcity. So here we are seeing that people are drilling deeper at a rate that is twice that of declining water levels. And so these patterns could be revealing risk aversion. People worried that groundwater levels are going to continue to decline. Now, for California, this is especially fascinating because recently in 2014, California passed the Sustainable Groundwater Management Act that was focused on bringing groundwater to sustainable levels. So of course, if we're talking about groundwater, it's really important to look at the lithology. That plays a huge role in understanding water availability and access, and also the depth to which people are drilling their groundwater wells. We got lithology information from the groundwater well reports that we analyzed that got us these data that you're seeing in the yellow circles here. And what we find is that this aquifer is a really thick aquifer, at least near Stockton, California, mostly sand. And so this subsurface profile really supports deeper drilling. And this is really going to play a role in what's happening in California. So we looked at what's happening locally in places like Stockton, California, but let's translate this information to a plot that can help us understand trends at a regional level. Across the x-axis, we have well completion depth. Anything that plots on the left side indicates a shallowing trend. Anything that plots on the right side indicates a deepening trend. On the y-axis, we have the water level trend. Anything that plots across the top indicates a rising water level. Anything that plots across the bottom indicates a declining water level. So let's bring in our example from Stockton, California to see where on this plot we would show up. Well, we know that groundwater wells are getting deeper over time, so we'd expect to be on the right side. We know that water levels are declining, so we'd expect to be across the bottom two quadrants. And sure enough, when we plot Stockton, California, we end up in those overlapping quadrants, here the bottom right-hand side. We could do the same analysis that we did for Stockton, California for entire regions. So here we're looking at the Sacramento Valley or the Northern Central Valley. On the left-hand side, you see a zoomed out picture of a satellite image where the blue dot again shows the monitoring wells and the yellow shows the buffers that we were looking at. And the buffer indicates which wells we would include in our analysis for deepening trends. When we do this for the entire region of the Northern Central Valley or the Sacramento Valley, what we find is that the majority of sites, actually the great majority of sites, 83% of sites, fall in this bottom right-hand corner where each site is again a monitoring well with water levels, in this case, between 2000 and 2015, and it's nearby constructed groundwater wells constructed during that same period of interest. So again, what's really neat about this information is that we can do the same analyses, not only for local areas and regional areas, but for aquifers across the United States. So the next few slides, I'm going to focus on these 5 key aquifers, chosen for 1, their importance, and 2, their geographic distribution across the United States. What you probably noticed is that we broke down the Central Valley and the High Plains into 3 different regions, and that's because of the extent of these aquifers. And what you're also probably asking yourself is, why are some of these aquifers colored a lot of different colors, while the Central Valley, for instance, is only colored red? And the reason for that is because the colors denote which state that portion of the aquifer is in. And one of the reasons why we wanted to highlight this is because if you think back to some of those earlier slides where we really highlight the biases in data collection by the different states and sub-state areas, it's really important to recognize which of these data are attributed to Nebraska versus New Mexico because of the different data collection processes that they have, but also when they started collecting data. So here's the example for the entire Central Valley. So we have the Sacramento Valley, the San Joaquin Basin, and Tulare Lake. And what you'll notice is that we are consistently falling in this lower right-hand quadrant. So 83%, 74%, and 89% of sites are in that lower right-hand quadrant, which indicates that we have deeper drilling matched with declining water levels. And so again, just to give you a visualization of what that would look like, well, that's the Stockton, California example. So groundwater wells are getting deeper over time and water levels are declining over time. I really like to highlight the Central Valley because the trends that we're seeing here are very unique, especially compared to the other aquifers that we're going to look at today. So if we move east towards the high plains, the first thing that pops out is that we are no longer clustered in that lower right-hand corner like we saw for the Central Valley. In fact, in the northern high plains, we're sort of scattered through all four quadrants, same with the central high plains. But it's really the southern high plains that I want to draw your eyes to today. So again, across the x-axis, we have this depth trend, well completion depth trends, and across the y-axis, we have the water level trends. And what you see is that most of the sites are spread out along the bottom two quadrants, indicating that in most monitoring wells in this portion of the High Plains aquifer, groundwater levels are declining. Now, the other thing that I want to point out is that we're not always clustered in that right-hand corner. And what that means is that we're not always drilling deeper groundwater wells when our water levels are declining. Now, this is especially the case for the portion of eastern New Mexico. And why don't we zoom in to an example like we saw for Stockton, California, but in New Mexico to sort of get a deeper dive of what's actually happening here. So we picked Portales, New Mexico, because it's a really interesting example. The blue area here, again, shows the water level time series. Over the period of interest, groundwater levels are declining at a rate of 3 meters per decade. These yellow circles indicate the groundwater wells being constructed in this area during that period. And what we see is that the rate here is only 1 meter per decade. And so folks are not drilling deeper at the same rate that groundwater levels are declining. And this is really fascinating because if we look at the lithology for Portales, New Mexico, what we see is that people are really bottoming out at this low permeability layer. And in fact, rather than a consistent deepening trend, we see that because there's nowhere to go, folks are even drilling shallower wells to compensate for the fact that, below this low permeability layer, yields are low, but also water tends to be brackish. So let's move our way eastward. Now we're going to focus on the Atlantic coastal plain and the Floridan aquifer system. We don't really see any clear trends happening here, and there's probably a number of reasons for this, but we really want to highlight here that it's probably because there's a number of confining units and the stratigraphy is really complex, much more complex than the Central Valley. If we go to the Mississippi and Bayman, also, very complex stratigraphy. What we actually see, though, is that there's some interesting trends that are mimicking what we're seeing in California. So 73% of monitoring wells are indicating that groundwater levels are declining over time. And what we also see is that deepening is 2 times more common than well shallowing. And so again, the big take-home message here is that declining water levels are not always being met by deeper drilling. And so our question, or the question that then arose to us, especially linking back to some of the earlier slides that I presented, is whose wells are most vulnerable to going dry if groundwater depletion continues. So here you see a shallow well that's running dry and a deeper well that actually has access to groundwater. And the question is, are there different purposes for these groundwater wells, reasons for which these were constructed that are really driving the deepening? And are there some purposes that are actually indicating that they're more vulnerable to going dry? So here you see a map of the median agricultural groundwater depth minus the median domestic groundwater depth. Just to break this down here, the blue indicates that the median depth within the grid that we're analyzing is deeper for domestic wells, and the green indicates that it's deeper for agricultural wells. Anything that's gray indicates that we didn't have enough data to run our analysis. And so there's some really interesting hotspots that we see here. In California, anybody who's familiar with California, this is probably not very surprising, but we have deeper agricultural wells than we have domestic wells. But in the Mississippi embayment, we have a different story. We actually have deeper domestic wells than we have agricultural wells. And so many folks in the audience are probably thinking, well, there's lots of reasons why people drill deeper groundwater wells. And I completely agree. You know, we have better technology, both pump technology and drilling technology today than we've ever had before. And that allows us to drill deeper groundwater wells. Some folks may be drilling deeper to avoid shallow pollution. So in Mississippi, we were really fascinated by these trends that we saw where domestic groundwater wells were drilled deeper than agricultural wells. And so when we dove into the literature, we found out that in the early 1900s, folks started drilling deeper domestic groundwater wells because they were afraid of typhoid and getting typhoid from the shallow aquifer. Regulation, and now this is particularly of interest to me because it hits on some of the work that I'm going to be presenting in a few slides, but what we're finding is that different laws could apply to deeper wells. So wells that withdraw water from deeper aquifers may be exempt from some of the really stringent regulations that are governing those shallow, unconfined aquifers. And our hypothesis here is that could be incentivizing deeper drilling. And those of you who could sort of think back to the depth slide, what you probably saw was a dark blue circle in South Dakota. And one of our hypotheses is that that dark blue, deep groundwater drilling is being incentivized because of regulatory exemptions. And then, of course, water quantity. So people could be drilling deeper groundwater wells in search for higher yields. The rate at which water can be pumped from some wells varies based on the aquifers that you're pumping water from. And some aquifers can have higher yields than other aquifers. And we also found in the literature that sometimes people are drilling deeper wells because of discoveries of deep formations bearing fresh water. And so regardless of the factors that are driving deeper groundwater drilling and construction, the question remains, is drilling deeper groundwater wells a solution or a stopgap? And we suggest that it's a stopgap, that it's an unsustainable solution, especially for groundwater depletion, for 4 key reasons. The first is that wells are expensive. And so I should point out here that there's actually not that much data about how expensive groundwater wells are. And it took, about a year working with an undergrad researcher to go through hundreds of different newspapers and pull out these data to get an idea of how much are people spending on drilling new groundwater wells. And what we found is that that domestic wells ended up being about tens of thousands of dollars. Agricultural wells tend to be about hundreds of thousands of dollars, and municipal wells can be more than $1 million. People don't have the money to drill the new wells, and that's the biggest problem. This is a quote by Jim Smith, who lost his well to declining water levels during California's most recent drought. And I really think this drives home one of the reasons why drilling deeper is unsustainable. It's unaffordable for some of the population. They just don't have the money to drill and construct new groundwater wells. The second reason is because of increased energy requirements. Well, we know that the energy requirements to lift water increases with every foot that water is lifted. Our data suggests that deeper wells tend to have deeper water levels. So not only are we being hit with the energy required to lift water because we have declining water levels, but as we drill deeper wells, we also have that extra lift that's involved with getting the water to the surface. Now, in areas where pumps are powered by high carbon sources, the combination of declining water levels and deeper wells could really increase the carbon emissions per unit of water pumped. And of course, that has impacts on the sustainability of drilling deeper groundwater wells. Reason 3, because sometimes there's nowhere to go. Sometimes we can't actually drill deeper groundwater wells. And we saw this in the portion of the High Plains Aquifer underlying eastern New Mexico. We had a low permeability rock formation, and then underneath that, we had brackish to saline water. And so in the central and southern High Plains, we found, or literature has shown, that this area is characterized by a thin saturated thickness, defined here as the offset between the bedrock and the water table. So this map here shows the difference between the well bottom and the base of the aquifer, where red indicates that the well bottom is within 20 meters of the base of the aquifer. And just to give you some visual perspective, pointing here, the bottom of the well and the base of the aquifer here, and throughout most of the central and southern High Plains is within 20 meters. We were really fascinated by what we saw happening in Portales, New Mexico. And so we actually dove into some of the local water management plans there. And this is a quote from the City of Portales review of water supply options. Deep groundwater is of low quality and also likely of low quantity. Things are looking pretty bleak here. And this report outlines potential options for actually importing water from outside the area. Which of course, when we import water from other places, that also requires energy for the conveyance and the distribution of that water. Reason 4, because we often have brackish water with depth. And so we know that groundwater gets saltier with depth, so it may not be feasible to use water without desal. And in a recent paper, we showed that in several sedimentary basins, fresh groundwater is less abundant than we previously thought. We also found in that same paper is that where we do have fresh water at depth, these resources may be threatened by pore space competition from the oil and gas industry. And so, I'm going to transition here from this idea that groundwater well drilling is an unsustainable stopgap to groundwater depletion by just really highlighting that this makes sense. But it helps to have 12 million groundwater wells to show these patterns at a continental scale. And the reason for this is because we have immense heterogeneity in both the subsurface, but also in the actions of our groundwater users. And so I'm going to move from the challenges to opportunities. What are we going to do about depletion? So the University of California, Santa Barbara had the good fortune of hosting Jay, who presented on water scarcity on Monday. And his presentation ended with a pitch. What are we going to do about it? And so from here on, I want to focus on some of the work that I'm doing to identify opportunities. And it starts with what we're dubbing the Western Water Dashboard. This is an online interactive tool that explores different legal options to manage groundwater sustainability. It allows you to look at the West as a region, individual states, but it also allows you to compare states and what they're doing. This work is inspired by California's 2014 Sustainable Groundwater Management Act. This is a really important legislation. It's the first time in California's history that the state has a framework for achieving sustainability in groundwater resources. And it requires local agencies to either increase supply, decrease pumping, or do a combination of both. A recent review of these plans highlights that many do not consider protection for domestic groundwater wells. The left-hand side here, you see an estimate of wells that went dry during the 2012 and to 2016 drought. And on the right-hand side, you see areas in orange and yellow that have not really put together a program to consider the impact on shallow domestic wells running dry. The review of groundwater management plans also found that a lot of different local agencies were emphasizing increasing supply, and a lot of them fell short on decreasing pumping. One of the reasons for this or one of the main critiques of the plans is that there was a heavy focus on increasing supply, but it wasn't necessarily clear where that water supply was going to come from. So where were they going to get water for recharge? Where was this reclaimed and recycled water going to come from to sort of meet the impacts from overdrafting the basin? And the review of these groundwater management plans really highlighted that there's this unrealized opportunity focused on decreasing pumping. So innovative techniques, policies, management to really figure out how do we reduce pumping. Now, this is not really too surprising to many people in California because California doesn't really have a background in managing the demand side. And so back in 2014, we sort of saw this coming and we started asking, what are other states doing to manage their pumping? Now, we specifically focused on groundwater permitting for new groundwater withdrawals. And this is really important because we thought that this would be a proactive approach, this idea of managing new pumping. We didn't necessarily want to get into how do we curtail current pumping. This is very controversial, and it also can have really big socioeconomic impacts on local communities. And so we thought that there was a lot of opportunity here to focus on new pumping and how to manage that. So new pumping without permitting, so without permission before pumping, sort of looks like this. You get a license to drill a groundwater well, you withdraw that water, and you have a right to use that water. Well, new pumping with permitting has this additional step, and that step requires getting permission from some local agency. And for those of you in the audience that are hydrogeologists, you're probably thinking, well, what does this really have to do with the physical science? And it actually has a lot to do with the physical science. So new pumping with permitting really allows hydrogeology principles to be integrated. It allows us to consider things like groundwater surface water interactions. It allows us to consider groundwater dependent ecosystems. And then those of you in the audience who are focused on social systems, it also allows us to integrate socioeconomic priorities such as beneficial uses. The key part here with permitting is that it allows us to be proactive and not reactive. And so the question is, how widespread are these controls on new groundwater withdrawals? And so, like I said, we spent the past 6 years looking through statutes and regulations, and we came up with over 275 distinct areas in the Western 17 states where each color on this map is indicating a different legal control for managing new groundwater withdrawals. Now, for me, this is a great way to sort of leave us in this presentation and begin our questioning, because what we see here is that groundwater regulation and this focus on controlling new groundwater withdrawals is widespread, representing that a lot of people throughout the Western United States are thinking about proactive management. And really, this leaves me with a lot of room for optimism that there are a lot of ways that people are using policy, regulation, legislation to manage new withdrawals. And so after collecting this information, we are now in the process of trying to figure out how do we distinguish successful from less successful legal frameworks so that we can give this information and provide, lessons learned, best practices to people who are trying to figure out what the best way to decrease pumping is in their area. And so with that, I'd like to close on a high note where I really believe that we are beginning to make the invisible visible. We have a lot of information out there, and it's by innovatively, weaving together both the physical system and the human system that I believe we're going to get to sustainable groundwater management.
Deb, thanks very much. Really stimulating talk. And I'm sure there'll be some questions here. As per usual, we will look for your questions in the chat. And Kim will be helping with that as well. And as I wait for questions to roll in, maybe I could ask one just on the shallowing. I was curious about that. And could that represent just new wells, putting more straws in the ground, and you're seeing that expressed through the shallowing data? Or is it truly, I mean, how do you take an existing well and go shallower? I'm guessing it's more straws going in the ground in that area, and what was it, just in the upper Midwest or where I saw the shallowing trend?
Yes. So each one of those dots was indicating a new groundwater well being constructed,
Yeah.
or an existing groundwater well being deepened.
Great. Still waiting for questions to come in the chat. What about, we look to the US and we see real division, red state, blue state. And with your groundwater regulations that you're showing in that lower right-hand plot that's there now, did anything emerge in terms of political leanings and maybe the nature of the regulation? Like, do you find a state like New Hampshire, saying you can pry that drill rig from my cold dead hand, whereas you've got states like California that are maybe a little more progressive because of the political leanings? Does that factor in at all?
This is a great question, and it's actually part of the current work that Rebecca Nelson and I are doing. You would assume that California is extremely progressive, and that it would be at the forefront of groundwater management. But in fact, it's actually a little bit more on the conservative side. And so one of the things that we're looking at is which states allow for a statewide or a state agency management plan, and which states are really focused on local control. And the two that I really like to sort of compare are Texas and California. And so, very conservative Texas, very liberal California, and yet both of them have sort of lagged in their groundwater management legislation behind some of the other states in the United States. And both of them really are heavily focused on this idea of local control, which has both pros and cons.
Yes. Okay, great. Okay, questions are rolling in now. This is from Colleen. There have been issues in the past with errors in the method of calculating sustainable yield. How adaptable would regulations be to continued depletion? What about historical water rights agreements between states, first come, first serve? Any changes to these regulations? If not, how do you ensure access for all?
Good question. Quite detailed, and so I'll try to do the best I can to boil down the big complexities that we're seeing here. So one of the things that we're fascinated in is how does using permitting, so getting this permission ahead of time, allow us to actually integrate the most current science? And so that's one of the benefits of using a permitting regime as opposed to traditional common law. It allows us, hopefully, to sort of adapt with time, and it allows us to take into account these really critical aspects of the physical science. And so the hope here, and what we're actually interested in, is trying to figure out how many of these different management systems consider things like safe yield, sustainable yield, and what does that really mean when they're actually giving out those permits? How does that play a role? And the reason for that, and I'm learning this, I'm trained as an engineer, I'm not trained as a legal scholar, and it's been quite interesting for me to learn that words can be interpreted in many different ways, and I'm used to numbers. 5 is always 5, but we have things like safe yield, like sustainable yield, that can be interpreted in many different ways. And so after we're done with this initial phase, the next phase is actually to figure out how are the people who are making decisions interpreting these laws, and what does that mean with regard to how successful these laws are.
Right. Thank you. Here's a question from Maria in Colombia, who's watching live. Hi, Maria. Here she's saying, here we have groundwater regulation that requires a permit for drilling and for pumping. But since government agencies are very affected by bureaucracy, permitting takes forever and productive projects are affected by this. How do you prevent this from happening?
That's a really good question. So in most of the states, at least in the West, you do need a permit to construct a groundwater well. There are some exemptions to that. And so we also have, so there's the permit to construct a well, permit to withdraw water. What we're finding is that it sort of really just depends on who's making these decisions. And that's why it's really important to get a better idea of the different folks involved in interpreting the different regulations. We've been working really closely with folks from New Mexico. And, what we've seen is that a lot of the managers there are just really passionate. They want to protect the resource, but they also recognize that groundwater is fundamental to local economies. And so I don't really, I don't know how that translates to Colombia, but I think that leadership really matters. And we're seeing that throughout the West. Yeah.
Here's one from Ghulam, and they're saying that in Pakistan, I think groundwater is contributing 50% for agriculture, if I'm understanding the question correctly, and almost 100% for drinking water. Extraction's increasing over time. Controlling the extraction is socially and politically resisted. How to overcome this? I guess therein lies the rub.
Yes, and I think that's hopefully in 5 years I'll have an answer for you, or I'll have some case studies that really show how to get beyond some of these controversial regulations. And that's one of the reasons why we're focusing on the new groundwater withdrawals and not necessarily curbing historical groundwater withdrawals, because I think that's where the real opportunity is to get ahead and to create this management framework that sets the future.
Here's one from Mohammed, one of the students in the class you'll speak with a little later. He's talking about agriculture and particularly the kind of things you're growing. And he's giving an example of, a melon versus a cherry or different crops and how that affects kind of crop per drop. But do you think confining the farmers for producing certain products can work for controlling well levels? Which I guess it's a good question in terms of how to come at it from the other end.
Yes, and great question, also quite controversial. And so what I could tell you is the way that I think about this is trade-offs, right? So we can require certain farmers to grow certain crops, but there's trade-offs involved in that. And some of my earlier work looking at the water energy nexus actually focused on the social and economic implications of sort of redirecting farmers to change what crops they grow. And so what I know from that experience is that sometimes farmers are culturally attached to what they are growing. It's been done in their family for decades, sometimes centuries. And so, I can tell you that the research that I'm doing highlights those social and economic connections. But how I personally value that could be different than somebody else. And I think it really depends on the local area and the decisions that folks there want to make and what sort of trade-offs that they want to make in their priorities.
Well, one thing I was wondering through your talk was, the losing water into unfavorable formations. That might have been your phrase. I guess we would have maps of that at the U.S. scale. So can you make predictions, where, and even based on pump rates, how much time is left on the clock for, deepening and, really be thinking on a centennial kind of time scale almost to, where this is going to, really affect climate refugees or the need for uprooting and when we'll have those tipping points. Have you explored that?
Yeah, so Scott and I are both working in collaboration with Mark Bierkens, who is actually asking that question and similar questions. And we're hoping to use the information that we have about groundwater wells to sort of inform the models that he's working on.
Great.
And I think that's a really important question. I should highlight that in the United States, not all states require us to meter how much water is being pulled out. And so our estimates of how much water we're pumping are just that, they're estimates. They're not, actual information. And so that could be one tricky element of figuring out, how much time we have left with regard to declining water levels.
Great. Maybe one last question. And I think there were one or two questions early on that I missed. And, if you're not a hydrologist and you're not thinking groundwater, you might have a perception that, well, I go deeper, it's going to be purer or better in some way. But you talked about the brackishness of water increasing with depth. How do you I don't know, do public education in groundwater? Because I think in addition to being out of sight, it's not something that the lay public has kind of an intuitive feel for, maybe many misconceptions. And that is probably feeding into some of the, political regulatory issues. Any final thoughts on that?
Yes. So that's actually, part of this Western Water Dashboard. How do we take really complex information and put it into a visualization that the layperson can understand? How do we, create graphics like this to really highlight what's happening both above the surface and below the surface? And, this takes a lot of time. It's quite complex, but I do think that that's part of what we need to move us forward and get to sustainable groundwater management.
Yeah. Awesome. Deb, well, on behalf of the Global Institute for Water Security and the Global Water Futures Program, I'd like to thank you so much for your time today. This is really a stunning talk. We're going to end this this part of the day's proceedings, and for the students taking the class for credit, plus Deb, we'll transition to Zoom. Don't forget, everyone, that we have Ross Woods coming to us next week from Bristol University in the UK. And big round of applause for Deb. All right. Thank you, everybody.